what I wanted to do was tell you a little bit about what I do. And then hopefully, maybe some of you have ideas of things that you could help me with or collaborate with me on. In the long term, I want to know what you guys do. So some people have presented already, so I can see if there's any opportunities for us to collaborate on your stuff as well. So I find a lot of people are, I tell them what I do, and then they start asking questions, and to give an appropriate answer requires more than 30 seconds. And then I would end up saying the same things again and again, and then people start, people ask lots and lots of questions, which is good, except, usually people don't, if they're just coming up and asking you, they're not ready to spend half an hour discussing the topic. It was just curiosity, right? So hopefully this is the opportunity for me to tell you a little bit more about what I do. So I want to say that what I do is forensic inference and statistics. However, if you push me, I go back to what's my technical background. My technical background, I was trained in many different things actually, but my PhD work was in phonetics, and I did statistical modeling of speech data. I was at that time working in speech perception primarily. And then I was doing a postdoc, and I saw a job advertised which was doing forensic voice comparison, and it was exactly the same skill set. It was the opposite research question, if you like. So speech perception, differences between speakers is noise, and you're interested in the message. Forensic voice comparison, it's the differences between speakers is the thing you're interested in. So that's how I ended up getting into this field, and then I got very interested in evaluation of evidence in general and forensic inference and statistics, and eventually I'm here. So speech is very different from DNA. So I'm going to go back, very introductory stuff on phonetics, and do interrupt me and ask questions as we go along. You've heard me talking, and you probably don't pay any attention to the fact that I'm a human who is speaking, and then you're decoding that message. But if you are interested in phonetics and you're interested in that transmission, how do people actually articulate? How does that sound travel through the air? How do people decode that through their ears and their brain? And so some of this is going to be helpful basic knowledge to understand what my data look like. And when I say I think the data I have, I think looks very different from DNA data. But I think the data I have actually looks a lot more like data that you might get in lots of other branches of forensic science. Probably more branches of forensic science, I would say, likely have data that look more like speech data than like DNA data. So let's see how good I am at drawing. I haven't done this for a long time. It's a crocodile or something like that. Okay, we have a bottom bit. Some funny stuff going on down there. Okay, we need something going on up here. We need something going on here.
It's not a crocodile.
It's not a crocodile anymore. This is not to scale.
It's a boa constrictor.
Right.
An elephant.
Not to scale. Okay, I'm gonna do some simplifications because there's two tubes down here. I'm only gonna draw one, and nothing is to scale or necessarily quite in the right place. Right. Okay. Imagine that a ninja came in and chopped your head in half, and that's what we're looking at. Right, now it makes sense? Okay. So this is kind of a two-dimensional representation of the human vocal tract. Right, lips, teeth, this is the tongue. Right, if you think about your tongue, you think your tongue is flat, yeah? Because when you stick it out, it's kind of flat. But in fact, the tongue is more kind of like a round ball thing. This is the uvula. That's a little bit at the back. This can go up and down, right? And then this is a passage. This is actually very complicated up here, but this is your nostrils coming out here, right? So this can open and close. Your tongue, you can move your tongue around in your mouth. You can stick it out. You can move it up and down, backwards and forwards. You can open your jaw, right? Down here, this is the thyroid. So there's a thyroid cartilage, there's a cricoid cartilage. In between those stuck in between those are the vocal folds. Right, so how are we going to make speech sounds? So let's start with the vocal folds. The vocal folds are like the reeds on a wind instrument. Or if it's a brass instrument, the player actually vibrates their lips. So is anybody a musician? Anybody play a wind instrument? Flute? Oh, gee, that one's difficult. that one's complicated. It's anybody play brass or woodwind? No, okay. Good, I can say whatever I want and I won't be contradicted. Okay, a brass player actually vibrates their lips. The brass player pretty much goes into the embouchement, I think it's called. Right, so, and in fact, what's happening down here with the vocal folds is really, from a physical perspective, it's exactly the same as going, right? And I can go at a fairly low frequency, or if I put more tension on my lips, I can go, and that's a higher frequency sound, right? And I'm not very good at controlling that in my lips. If I were a brass player and I had a embouchement in front of me, I could probably do finer control on the exact frequency of vibration there. But I am really good at changing the frequency of vibration of my vocal folds. So I can speak with a high-pitched voice, or I can speak with a low-pitched voice, or somewhere in between. And how do you know if somebody's asking a question? Basically what you're doing, you've got muscles that can basically control the tightness of your vocal folds. Then you have, this is basically, you can treat as a complex system of tubes. Right, so back to the wind instruments. Let's say a trumpet versus a tuba. Or an oboe versus a buffoon. No, a bassoon. Anybody play the buffoon? Or you could think of other things, flutes. You've got little flutes, piccolos, or really big flutes. Right, what happened? Or pipe organs, little pipe organs, big pipe organs, or even, it's a little different, but strings and a piano. Right, the long ones vibrate at lower frequencies. Right, why does a tuba sound very different from a trumpet? It's got a lower frequency. Right, and it's the vibrations. It's actually the resonances in the tube. So the long tube has lower resonances than the high tube. And the short tube has high resonances, and those change the properties. But you've got something vibrating first, a reed or the lips, and then you've got your tube, and it's longer or shorter. Well, a human, here's the vibration here, the vocal folds, and then your tube. You can actually change the length of the tube. If I do that, put my lips out, my tube. Vocal tract tube got longer. I can actually lower my larynx, right? So this can go up and down a bit. So I can make the tube longer and shorter, but it's kind of limited to how long and short I can make the tube. But what I can do a lot of is I can move my tongue around. I can open and close my jaw. I can open and close this extra tube here. And I can change speech. I can change the resonance properties of my speech by making those sorts of changes. So, these vocal folds, I can change the vibration of the vocal folds. And does anybody sing? Is anybody a singer? You're a singer? Okay. Can you, pick a...
Yeah.
Okay, let's pick it. Just pick one vowel. Let's say ah. And can you sing ah? Can you sing different notes?
Yeah.
Right. Was everybody looking? She didn't. Basically, she didn't change the shape of her mouth. That stayed fixed. What she changed was the resonance. Was not the shape of the mouth, but the vibration of the vocal folds. Right. So when you're singing, what you do is you change. Basically, you change your muscle tension on these, and you're changing the rate of vibration here. But if I say ah, I'm not going to change. I'm not going to try and change the rate of vibration there, but I can say ah. Now I'm going to close my mouth. I, or the other way. Yeah. Right. So you should have had e, a. Right. So the different vowels that you hear are not due to differences in vibration here. They're due to differences in the resonances, which are caused by me changing the shape of this supralaryngeal vocal tract. And basically moving the tongue backwards and forwards, up and down, it's attached to the jaw, closing, opening, closing this. Okay, those are all voice sounds. I can whisper. If I whisper, then I'm not making vibrations here. But what I am doing is pushing air very quickly through my vocal folds, which causes turbulent flow. But I can also cause turbulent flow at other places. I can go tss. Right? What I'm doing is I'm pushing air very quickly through a gap up here. Tss, and it's actually hitting the tongue. It's hitting the teeth there. I can go shh, which I've got my tongue in a different place, but it's the same mechanism for creating that turbulent flow, and then you can hear different sounds. Right? And opening and closing, so b, m. Okay, that was opening and closing this. B, m. If you wrote a B or an M, well, the difference in pronunciation terms is whether you had this raised or lowered. Okay, so that's very basically human speech production. What has this got to do with forensic voice comparison? So usually forensic voice comparison, I'll give you a typical scenario. There's a telephone intercept, and the police have an interview with a suspect. And you get to court, and the court wants to decide, is the person on the telephone intercept the same person as is the defendant? And we have a recording, or when the police interviewed the suspect or charged them, and they recorded that interview, and we have a recording. We know that is a recording of the defendant. And this recording of the telephone intercept, the court wants to decide who is speaking. So how does all of this help us? I might say, in fact, it doesn't, but it lets us understand why we have differences between speakers. We're interested in differences between speakers. So adult males generally have more massive vocal folds and generally have longer vocal tracts than adult females. Right? So if you think about it, adult men have lower pitched voices than adult women. Children have higher pitched voices. They have smaller vocal folds. But the other thing is the vocal tract length. So that's the basic rate of vibration, but the resonances are also different. Adult males tend to have longer vocal tracts, therefore lower resonance frequencies as well. Okay, so also basically, so we talked about, adult males versus adult females versus children. These they're gross physical differences within adult males, within adult females. There's going to be differences in the physical attributes from person to person. There's going to be anatomical differences, and that is one source of between speaker differences. But another very important source of between speaker difference is behavior. So, how many people can speak more than one language? Right. You sound different when you speak a different language. You haven't changed your anatomy. You've changed your behavior. right? But okay, well, we have behavior, but we have all sorts of other behavior. Probably, you know, the way you talk to family and friends is different from the way you give a formal lecture. Sometimes you whisper, sometimes you shout, and there's all sorts of potential subtle things in between those. Maybe you're sad or happy, all of these behaviors. So speech is not, if we're doing forensic voice comparison, we're not just looking at anatomical, physiological attributes. We're also looking at behavior. Right, so I think in that sense it's quite different from DNA. And to complicate things more, so transfer mechanisms. So most of these things that we get to analyze are recordings. We're not actually analyzing speakers, right? So I'm using the term forensic voice comparison. It's not exactly accurate, but I don't want to use forensic speaker comparison because it would be like fingerprints would be toucher comparison. Forensic analysis of voice recording. So, and I try to avoid speech because then you think Gettysburg Address versus I Have a Dream. So no term is perfect. That's just what I happen to use. So often what you're getting is the effect of the environment. Well, this speaking style, and I'm actually projecting a bit now because I'm speaking to a room full of people. I'm projecting. Right, so that makes me speak differently than if I were just talking to one person in a quiet room. Imagine you're in the cafeteria at lunchtime. What do? It's a technical term, it's called lombarding. It's the Lombard effect, where people speak, and it's not just speaking louder. It's speaking people are deliberately speaking in a way which they think will make it easier for the person they're talking to understand them. Right? It's not just loudness, it's other things that have to do with clarity. Right? So there's all these behavioral things in the environment that may affect how you're going to behave. This room, I walk into rooms, and you probably walk into rooms and you don't notice things that I notice about the acoustic environment. So this room actually has a substantial reverberation. You can hear that. You can hear this, right? We've got hard walls, and in fact, I think I was sitting about there once, and I spoke, and boom. This room actually has a focal spot, I think around right there, because of these hard walls, and it's semicircular. And if you sit in a different part, you try it later. Go sit in different parts of the room when nobody else is here and just speak, and you'll discover that there's a spot where you get all of these echoes coming back to you. The other thing I noticed acoustically in this room is the noise of the fan in the projector. Often, police interview rooms are little tiny rooms with hard walls, loud ventilation, non-ideal environment.
And neon noise was new. The light.
Lights, oh yeah, okay, the lights, maybe fluorescent lights may be making a noise. Okay, what about the other side? Often we have telephone recordings, right? Telephone, okay. You know people don't sound the same on the telephone than they do when you're speaking to them in person, yeah?
Or even if you're listening to them speaking on the telephone very often, in the same room.
Mm-hmm.
A lot of people have a telephone.
All right, so that's, oh yes, I have my telephone voice for speaking on the telephone, yes. Right, so that's behavior, but forget about behavior, even if they're saying exactly the same thing. Right, okay, telephones do things to, okay, so we have an acoustic signal, so coming out of here is an acoustic signal. Right, what's the acoustic signal? It's vibrations in the air. Right, and it's little tiny vibrations backwards and forwards that propagate. So okay, I'm not projecting to you by breathing out really hard so that my breath hits you. Right, and if the wind is coming past, unless if it's really windy, you can't hear me, but if it's just a little bit windy, my speech you would think, oh, isn't it just going off with the wind? And it's little tiny vibrations backwards and forwards. So these molecules here are vibrating, which are pushing on those molecules that are vibrating, which are pushing on those molecules that are vibrating. And eventually it hits your eardrum, right? And then that vibrates your eardrum. And then that's attached to a bunch of little bones, which then vibrate another drum, if you like, a drum surface, a membrane, which is on the opening to the cochlea. The cochlea is filled with fluid. So this eardrum out here, then the bones, and then vibrating the window on the cochlea, that whole mechanism is mostly an impedance matcher. So if you are, who swims? What? Dutch people swim. I know Dutch people. Okay, if you go underwater, try this. Go underwater, get somebody standing above the water to speak to you. Can you hear what they say? You can hear some of what they say. You can hear low frequencies, probably. But high frequency. It's, in fact, what happens when the sound waves hit the boundary between the air and the water, most of it gets reflected back. Right, so this mechanism, these bones are to match the impedance so that it gets into this fluid-filled area. And then inside, you have a cochlea, which looks like a snail. Yeah, it's got kind of a snug, it's got antenna, and no, it doesn't. But if we unroll it, if we unroll the cochlea and we say there's a window there, it's actually, there's two windows. It looks something like that. There's some stuff going on in here. There's a complex mechanism, but basically there are nerves coming off here, which go all the way up to your brain. And very basically what happens is that you get different parts of the cochlea vibrate in response to different frequencies of incoming vibration here. Right, so you've got vibration at a particular frequency, like say 1 kilohertz, and the nerves around this area, this part of the cochlea, fire, and they send the message up to your brain. So eventually your brain, and these kind of all stay in parallel, and so then your brain has kind of a row of response to different frequencies.
The vibration only enters up or both versions?
You've got your mechanism, which is connecting to your bones. Your eardrum is here.
And down is closer.
And this guy here's his pinna. And there's an opening. This is an opening, and there's actually an opening. It's the eustachian tube. It opens actually up here somewhere. Right. If you do that, blow your eardrums out. You need to do it when you're on a plane and the pressure's. You've actually got a tube. So there's the outside of your eardrum, the inside of your eardrum, there's air. And then there's a eustachian tube, connects that to the back of your throat. And so that you have a mechanism to equalize the pressure from outside and inside your eardrum. If you can't do that, then what happens is the pressure changes outside, your eardrum bends, and then when it's fully bent in, it won't vibrate anymore. Or if the pressure drops outside, then it's fully bent the other way and it won't vibrate anymore. And if you have a cold and your eustachian tube is blocked and you fly on a plane and the pressure suddenly changes, that's very painful. Right, but basically what we've got here, so let's say this one responds to 100 hertz, this one responds to 1,000 hertz, this one responds to 10,000 hertz. Right, we've got a frequency analyzer. So the recordings we have, they don't have an eardrum, they have a microphone. Right, but basically what's happening with the microphone, there's different designs, but let's think of a very basic microphone. It's got a, what's it called? It's got a kind of membrane. I think there might be a technical word for that. It escapes me. Okay, it's got a kind of, so your eardrum is a membrane. It's got a kind of membrane. And attached to that membrane, let's say there's a magnet attached to that membrane. So the air comes in and it vibrates this membrane. There's a magnet attached to it. So the magnet is now moving backwards and forwards. Right. So, really what you want is a very large surface area to collect as much sound as you want. So, because, if you're physically moving in a magnet, it has physical mass, and that's difficult to move. So you've got the magnet vibrating backwards and forwards. And then what you have is a coil of wire around the magnet. And if you remember your high school physics, if you've got a magnetic field that's now going backwards and forwards inside a coil of wire, that's going to induce a current in the wire. Right? And it's that current in the wire which is then the actual recorded signal. Right? So we have electronic signals, is what we care about. So you've got a microphone in your telephone. It's very tiny, it's not, right? Its actual design features may be kind of different from what he said, but there's a microphone in there. That's not the end of it, because we're still thinking about an analog signal. Right, so this gets digitized. So we can think about time, and we can think about intensity, and we've got some sort of speech signal. Right. So this is now we're thinking about, we could be thinking about the vibrations of the eardrum, or we could be thinking about the vibrations of the microphone, or we can now be thinking about the current induced in that coil is now, the intensity of that current is going up and down as that magnet is moving backwards and forwards. Right. This is still an analog signal, but in your telephone, very quickly, what happens is that gets turned into a digital signal. So what it does is time, instead of being continuous, it now says, okay, once every, now there's different sampling frequencies, but we're in the order of say 10,000 samples per second. So I can't draw 10,000 samples per second. Let me enlarge this a bit. Let's say this is part of that bit. So what I'm going to do is cut this up into, so I'm going to sample 10,000 times a second. And at each point in time, I'm going to say, what's the intensity? How high is that? So I don't have to record the time because I know I'm sampling at a set rate. Right? So I just have a string of numbers. And the number is, whatever this number is, 1, 2, 3, 4, 4.5, 4.5, 4. I just end up with a string of numbers. And if I know what the sampling frequency is, I don't need to record it. Or I could just have one tag that says, oh, the sampling frequency is 10,000 samples per second. If you play it back at the wrong frequency, then it's too fast or too slow. And if you listen to it, you immediately go, oh, I'm playing at the wrong sampling frequency.
But those numbers are not recorded to infinite precision, so they're
no. So
as well.
Those numbers, yeah. So those numbers, so it's 16 bits, for example. And we're going to have, it's these numbers like 1024, and we have some. So basically, what people do when they're designing communication devices is they want to transmit as little information as possible, so that they can they can either transmit that information faster or transmit more signals at the same time. So there's always going to be a trade-off between what your frequency of sampling is and what your quantization is. Right, so these are not going to be, so let's say, this is a kind of bad, but let's say I'm allowed 1 and I'm allowed 2 and I'm allowed 3 and I'm allowed 4. I'm not allowed 4.5. So this one I either record as 4 or I record as 5. Right, and I designed the system so that the listener at the other end still can understand what's being said. right? And maybe if I want people to actually sign up for my mobile telephone network rather than my competitors, and they like the quality that they hear, maybe I quantize more. That doesn't really work because everything's standardized. But standards evolve over time, and has anybody had a mobile phone for like 20 years? Is the quality not the same one? Like you keep replacing it, and you've got a better one now than you had before, and you can understand people better now than you used to be able to. Right?
They say that Nokia had the best sound quality.
Yeah.
That's what they say. I don't know whether it's true.
Mm-hmm. Right. So some of it is
My old one easier than my
Yeah.
new one. Yeah.
some of it is the quality of the microphone and the quality of the speaker, but other parts of it are how much information you're actually sending. And in fact, modern mobile telephone systems actually change the amount of information they're sending depending on what's happening at a particular time. Lots of people want to use this tower. I'm going to drop the amount of information that I'm accepting from each person. And the quality goes down. Right, so we end up with this. Now, this is now digital signal. Most of the work we want to do is, so here we had a frequency analyzer. We were saying what are the frequency components. So this signal that I've drawn here, you can see that there's some repetition in this signal. Yeah? So there's kind of a repetition about there. Maybe that's what we'd call the fundamental frequency. And then we have harmonics. Basically, a complex signal like this, we can decompose into a set of simpler signals, and we can make all of these sine waves. So we've got a simple sine wave, and then we have, say, another sine wave of another amplitude. And another frequency. And if I add those together, I get a more complex signal, something like that. And basically what I do is if I add lots and lots of simple sine waves together, I can make any arbitrarily complex sound up until I get to my quantization level. So I've just drawn 2, but you can draw 3, 4, 5, and you can make a more and more complex signal. So what we do is Fourier analysis, basically. We're going to do Fourier analysis on this signal, and then we're going to decompose this. If you wanted to make this signal out of a bunch of sine waves, what would be the frequency of each sine wave, and what would be the amplitude of each sine wave that you'd have to put in? And then generally the system then has actually your choice of frequencies gets fixed, and it's only the intensities you end up worrying about. And you don't worry, and then you don't worry about the phase either. But basically what we're going to do is we're going to do spectral analysis. Okay, life is complicated. Okay, I show you this signal. The signal we have is long, really long. And we've got 10,000, maybe 10,000 samples per second. What we tend to do is, the signal changes as well, speech changes, if you notice that. It's not it changes a lot. Right, so what I do is I take this signal, and let me use a color. Ooh, how exciting. And I do something like I take a window, which is, I multiply this signal by that window, and I do the spectral analysis on that window. Then I move this window along, and I do another spectral analysis. And I move the window along, and I do another spectral analysis. So what I end up with, I think I need some more space. So now what I end up with is I'm going to have frequency on this dimension. I'm going to have some sort of intensity on that dimension. And I'm going to have I'm drawing it as a continuous. Obviously, it's a set of discrete numbers. And at one point in time, I have this. And generally what I do then is I'm going to simplify this even more. I'm going to fit like a Fourier transform. I'm going to fit a discrete cosine transform to this. the same basic idea, deconvolve this into a bunch of simple curves. And I'm going to take the coefficient values for how intense is each of these curves. So that I'm going to convert into a set of numbers. I'm going to have a vector of numbers. And usually this frequency, we scale this in, instead of in hertz, we usually scale it in something called Mel, which is similar to what human perception is like. And then we fit a series of simple curves to the discrete cosine transforms. And then we see what's the intensity of each of those curves that I would have to put in to make this frequency, this spectrum, and then I write down the coefficient values of each of those. I move my window along in time. So this is time now here, and I get another set. Right, so all this is doing is it's telling me what the spectrum is. We're now getting to about 14 numbers here. But we're often sampling at say, 100 times a second.
You mean the window's moving?
Yeah, the window's moving. So the window might be 20 milliseconds wide and it moves 10 milliseconds. Right, so we get 100 samples per second. And then we have, say, 14 numbers here. Usually these get augmented with other things. Well, I'll not get into the details. These are typically called Mel frequency capsule coefficients.
And the window is really bell-shaped or
Yeah,
it's a square?
It's bell-shaped.
There is a reason
Yes,
to overlap.
to avoid transitions.
Yeah, okay.
You get artifacts. If you put a square and you get an artifact at the edge. Right. So what okay, I should mention I'm talking about a specific approach here, which I would generally label an automatic approach, right? Where we are just going to zap the whole speech signal. We might do some pre-processing and make sure, oh look, we're only going to actually measure the parts that belong to the speaker we're interested in. So we're going to get rid of the dogs and cats and other people speaking and the truck driving past, and we're only going to and silence because we're not interested in silence. We're going to try, okay, first identify the bits of the speaker that we're interested in, but then we're just going to zap everything, right? So one of the things that it gets augmented with is what they call deltas, which is the amount of change from here to here. So because at the end of the day, we end up ignoring time as well. But if we put in, usually it's done over a series of 5. What's the rate of change in this series of 5? And then we add that to make the vector longer. Those are called deltas. So those are the data. We end up with thousands, tens of thousands, hundreds of thousands of feature vectors.
So when you say ignore time, you don't mean you don't ignore order?
So the standard models that get used for this ignore, yes, they ignore time, they ignore the order in which they're right. One way to keep some information about time, right? This is not all models, but it's kind of like the standard way to do it. One way to keep some information about time is when we have okay, we've got 5 of these. We're here. This tends to be done on just one of these. So we're going to look at this one. Let's say that was 1, 2, 3, 4, 5. Let's say it's just linear. That one is linearly rising. Right? What we're going to do is we're going to go here and we'll say, what's the slope over these 5? Right? And then we'll append that slope. So that slope is 1, I guess. And then we're going to append that as to this vector. And we're going to do the same for the second coefficient, whatever that is. Right? So that then we're maintaining some information about local changes. And that's useful. Right? But in general, we're now going to throw this into statistical models that ignores what order these were in originally. That's a standard. It's a standard way of doing it.
Is that good?
empirically, it seems to be the most effective way to do it. People are always playing with okay. There are people who say, "No, you have ignored all that information. That's terrible." And there are people who try to do this, but at the end of the day, what works best? Okay, statistical modeling. Okay, those are what the data look like. Okay, I'll tell you about one. Okay, what's one model that we use for dealing with this? Okay, so first of all, we do stuff. We often, remember I said we have mismatches between, let's say, the telephone intercept recording. Maybe it's a different speaking style. It is being transmitted through a telephone. The other thing is often when people record telephone calls, they want to save space on their disk, so they compress it. It's like MP3. It's not always MP3, but if you know MP3 files are smaller, well, you know what? They get smaller by throwing some information away, right? They try to throw information away that the human listener doesn't notice. But if you're doing acoustic analysis, that might have been very important information for distinguishing between speakers. And on the other side, we've got the reverberant room with the air conditioner going. So there are techniques that are applied to at this feature level to try and compensate for some of those differences. Our basic model, a basic model, is to take all of these vectors. We need a sample of the relevant population. So we're going to calculate likelihood ratios. Okay. I'm going to pick, I don't know why I'm picking on Dutch people today. Right. So let's say we've got the voice on the question speaker recording. And everybody listens to that. Okay, let's say prosecution, defense, everybody agrees it's a male speaker, adult male speaker, and they're speaking English, and they have a Dutch accent. Right, so let's say that's that's the alternative hypothesis. It's not my client, it's some other adult male Dutchman speaking English. Okay.
Pretending to be Dutch.
Yeah, okay, well that's...
Pretending to be Bart.
Let's keep it simple. Right. So what am I, okay, and Bart is the suspect.
Yeah, of course.
Right, but Bart has been arrested and he's now on trial for phoning in the bomb threat to the Newton Institute.
It's getting better all the time.
But okay, let's say everybody has accepted that a reasonable alternative hypothesis is it's not Bart, it's some other Dutchman who is speaking English. Right. So I'm going to need to get a sample of Dutchmen speaking English. Right. And I'm going to want them. I'm going to want them with the same sort of. If he was shouting, I want them shouting. One of the things we did in Australia, we collected a database. We've got about 500 Australian English speakers, about half male, half female. We recorded them in different speaking styles, but we recorded high quality audio. And then what we do is we simulate things like what was the telephone channel. We can add in background noise. We can add reverberation.
So how do you decide who to pick? Yeah. That feels really critical.
Who decides?
Okay. Well. Let's say in this case we want a sample of adult male Dutchmen speaking English. Right. So this is from my perspective, this is the number one problem in forensic voice comparison today is not technological. It is having suitable data. Right. And data collection is really expensive. And having data that reflect the relevant population for this particular case is difficult.
If cost out was no issue in time, what would be the best?
For this case that I just invented, I would be I'd be trying to find as many Dutch people as possible and get recordings on
And
them.
you don't care about age, don't care about anything.
I may, I may.
It's not just a question. It's not just a question of getting recording. It's getting recordings in as close an environment to the one that the recording of
Yes.
the voice was made.
Right, and this is an important issue. How close is close enough?
Yeah, exactly.
How close is close enough? And that's what I always say. This is a pre-empirical question. How close is close enough? I think is because I'm going to collect data which I'm going to use to train my statistical models, and I'm also going to use data to test my statistical models. Well, you know, is that test meaningful? Are the test conditions? Is the population and the test conditions, are they sufficiently similar to the case that the results of those tests are meaningful for this case?
Yeah.
So now, in the first instance, if I'm the forensic practitioner, I'm going to make my judgment that I think these are sufficiently similar, that I think this is a valid thing to do, but that's my subjective opinion. And ultimately, I think as a fact of law as well, ultimately, it would be the trier, it would be the judge in admissibility hearing or the trier of fact of trial who gets to decide, well, is what you did really sufficiently similar to the conditions of the case that the results of those tests are meaningful? And I would expect that, and then basically I write this in my report, and I would expect that if I am instructed by one party, that the other party is going to dispute whether my data was sufficiently representative of the relevant population and of the particular conditions. And I think that's totally appropriate. The approach that I work in is, after this stage, I am going to do quantitative measurements, statistical models. I'm going to test the validity and reliability of my system. And I'm then going to take the question speaker recording and the non-speaker recording, run them through the system, get the answer, and directly report that answer, that likelihood ratio answer. So it's the system which I already validated under these conditions. And I'm not going to take the answer out of that and go, now, what do I think it means? If I did that, if I now made a subjective judgment on top of that, then that would be my system would include that subjective judgment at the end, and that would be the system I would have to validate. So the solution that we adopted when we were collecting our database in Australia was that we selected, okay, we were in Australia, so we collected Australian English speakers. That made on the assumption that that would allow us to do the largest proportion of cases. Now there's lots of people in Australia who speak languages other than Australian English and who speak English with accents other than Australian accents, and there are lots of crimes committed by people who are not Australian English speakers, but it seems to make sense as that's going to allow us to do the largest proportion of cases. We then also collected 3 speaking styles, which we thought were common speaking styles in forensic work. So we have the police interview style. It's a simulated police interview. We didn't really arrest people. We have a conversation of the telephone style, and we have an information exchange of the telephone. So that task was actually we have 2 people speaking at the same time. They each received a fax. So we're still relying on people to remember what faxes were. They each received a fax, and some of the information they can't read. So they have to call their colleague and say, hey, did you get this fax as well? I can't read some of the information. Can you tell me what's there? And it turns out that their colleague also has received this fax, and bits of the fax they can't read. But usually, by putting it together, they can fill in the information. So we end up having lots of letters and numbers and confirmation backwards and forwards. And that, in fact, is a very common sort of speaking style in things like fraud. And there's all sorts of tricks, like you have to make them write it down. If they don't have to write it down, they don't listen to the answer.
Just another question.
Yes.
So if you're interested in a panicked call on a 999 call, say, compared, would you look at would there be any difference between that and a calm, let's say a calm threat versus a panicked call? I'm not saying compare those,
Right.
but let's say you have a crime where there's
A priori,
calm threat
yeah.
versus a panic call.
Yeah.
Would that change the database you look at?
A priori, I would expect that would make a difference.
Yeah, me too.
Right. Okay. And in that case, let's say we have this mismatch. in that case, I would say, and I think this is going to make a big difference to the performance of the system. I would say then we have to try and get recordings with those speaking styles. I think speaking styles is something that we can't simulate.
Yeah,
Right. Our database, we recorded all of these with high quality audio. Because things like putting it through a telephone line, adding no background noise, we can simulate. And that was a kind of a practical solution to part of the problem. But the population, what is the relevant population, and gross speaking style differences, I think we can't simulate, so we need to collect them, and that's why it's difficult. Then we say, well, how, is talking with a friend on the telephone versus answering questions to a police interview, is that difference big enough to make? Is that important? I don't know. Right, so we need to do one of two things. Either we just need to say, okay, let's assume it's important and we'll collect data under those two conditions, or we need to, first of all, collect data under those conditions and run some validation tests. And if we discover that the difference between if you have this mismatch or if you don't have this mismatch, let's say we discover that that difference is negligible, right? And in the future, we don't need to worry about collecting both of those. We only need to collect one of those. And that would be very advantageous because it may also mean that sometimes there are existing databases that we could then use. But I think there's always going to be things like panic versus calm, where everybody's going to say, yeah, I think that's going to make a big difference, and we're going to need to have those data.
yeah, you could.
Yeah.
That's what you need to
This
do.
one, you can sample 999 calls to get a pretty good database on that. But most calls would be,
Right.
stress.
Yeah, that.
Okay, here is the other problem with relevant data for forensic cases. So first of all, we have to get the population, we have to get the speaking style, we need to get multiple non-contemporaneous recordings of the people that we know to be the same individual and not to be any other individual. So this is for our data collection, for testing, or for training. Right? So what we need speaker A at one point in time. Now, because here's the problem also. Let's say we've got a case, we've got this mobile telephone intercept, we've got the police interview, they didn't happen the same day. Maybe there was a week or a year or something, there was time. Usually time has elapsed between the recording of the question speaker being made and the recording of the non-speaker being made. So we need to get a recording of speaker A in some speaking style. Let's say we've got speaker A in the telephone style, and whatever speaking style and whatever recording condition. And we've got speaker A again in the interview speaking style. Right? And in fact, usually we want, to build better models and do better testing, we want maybe there's at least a week between each of these. This becomes an issue. In the case, well, how long do we think there was in the case between the first recording and the second recording? Was it a week? Sometimes I get people contacting me saying, yeah, we've got this recording from 20 years ago, and we've got a suspect. Imagine trying to collect those data. You want to find the existing data, but then here's the problem. Lots of existing databases don't have these multiple non-contemporaneous recordings that we know are the same speaker. They don't have the speaking styles that we're interested in for this case. And sometimes it's difficult to even figure out if, do we think this person is the right population? So there's all of these, when you combine all of these problems, it's like, we have to get the right population, we have to get the right speaking styles, we need to get multiple non-contemporaneous recordings, because if you, when we do our recording sessions, we collect telephone and interview, and I told you 3 speaking styles. We collect all 3 speaking styles at the same time. Right, but if we compare this with that, there is less variability. So there's within speaker variability that tends to be less if, that was 10 minutes and then immediately after the next 10 minutes. There tends to be much less variability there than a week later, right? And, well, you can think about, when you get up first thing in the morning, is your voice different from in the afternoon than in the evening? If you've been speaking a lot, is your voice different from if you haven't been speaking for a long time? Well, there's those sorts of minute to minute, hour to hour, but there's also week to week, and then there's year to year, and people's voices will change over 20 years. And the other thing is your reference population, the way people speak may have changed. If you listen to, if you listen to BBC news broadcasts from the 1950s, okay, people don't speak like that anymore. Right. So it's getting appropriate data to do it. That's what I'm going to say. That's the number one problem. And then you worry about all these sort of sampling issues. Is this really a representative sample? Right. I get back to, is this good enough? And I think that's something that the has to be debated before the judge in the admissibility hearing, before the trier of fact trial. This is the approach I take.
What kind of model are you using in the end?
Okay, model, yes. Well, people keep asking me questions, so I have to. Right, models. So a typical model, I'm just going to give you one. There are more complex modeling approaches, but I think because of time, I'm just going to show you one. And if you're interested in others, I can tell you about others later. Right, remember our data. We have these vectors. Let's say we end up with something like maybe 28, could be 14, 28, 36 dimension vectors. And then we have a measurement basically corresponding to every 10 milliseconds. So we actually have often tens or hundreds of thousands of these vectors. We've got our sample of the relevant, let's say we've got our sample and we're now happy that this is a sample of the relevant population. How many speakers do we need? That's an issue. We've got a whole bunch of speakers. We're going to take all of those data. For this model, we're going to pool all of those data from all the speakers. We might want to make sure that we've weighed each speaker equally. So that, we maybe one recording, we have a 10-minute recording from one speaker and a 5-minute recording from another speaker. We don't want to give the 10-minute recording twice as much weight as the 5-minute recording. So we want to do some equal weighting. And then we just pull all of those data together, and we're going to build a Gaussian mixture model. Right? So, do I need to explain Gaussian mixture models? Are we happy? Okay. We've got maybe 28 dimensions. We've got maybe on the order of 1,000 Gaussians in the Gaussian mixture model. But we've got lots and lots and lots of data to train this. We've got millions, tens of millions of data points. However, those came from they were every 10 milliseconds. There's correlation all over the place. Supposedly there's not correlation because there's not correlation between the dimensions. There is, but there's kind of theoretical models to say that the way we have deconvolved the spectrum, it's like a Fourier transform in the first place is deconvolving, and we've got orthogonal, we're using discrete cosine transforms that are supposed to be orthogonal. We usually fit diagonal only covariance matrices. Right, so if you're fitting a Gaussian mixture model, you can fit a small number of Gaussians, and you can do full covariance matrices on each Gaussian, or you can do more Gaussians and do diagonal only covariance matrices on each Gaussian, and you can approximate the same level of fit. Right, so life is this is the way things get done. You look puzzled.
Are you modelling the speech of one speaker or the modelling the speech
At this
of all
moment,
speakers thrown together?
the population, our sample of the population. We've thrown all of these data together now. We're gonna, so, it's gonna be, I'm only obviously drawing one dimension here. We've got maybe 28 dimensions, right? But we're gonna end up with some probability density distribution. And we trained that using all the data from, so, and it's like, how do you calculate the probability for an allele in the population, right? You take a whole bunch of people and you see what proportion of your sample has that value, right? So this is a generative model, right? There's a probability density function now fitted to, let's say we had 100, we got a sample of 100 Dutch speakers and we got, 2 minutes, 2 minutes turns out to be, you don't get much improvement after about 2 minutes. We got 2 minutes from each speaker, and that means we've got tens or hundreds of millions of data points in this fairly large dimensional space. And then we've got this, and then we fit a Gaussian mixture model, which is now
per
generated.
dimension. For each dimension.
No, it's multi-variate.
It's only really multivariate if you've got a non-diagonal.
No, because
So within each group,
So-
you've got
I can fit, right, I can fit 2 Gaussians like that. Or I can
that's a
fit,
mixture of
that's 2, or I could fit 1 Gaussian like that
Yeah. And you're putting
to and these might approximate the same level of fit to the data.
and you're doing the right hand of those two.
Right. So usually the solution is to do the diagonal only covariance matrices, but to do a larger number of Gaussians. And that's just, there are reasons for this solution, and that's standard. Right. So, and in fact, we usually 1,000, something like 1,024 of these. Okay, what do we do now? Now we get our, this is our sample of the population. Remember recording conditions? Okay, we're going to try and do use some techniques to try and take account of the difference in the recording conditions. But one of the things we should be doing that I think is important here is we have the recording of Bart in the police interview room. We want these recordings to be the police interview room style of speaking and technical recording conditions from the police interview room. Right, we now take the recording of our defendant. We take the data from our defendant. We've got all of these vectors, and the standard way to do this is to take this as our, if you like, this is now our distribution of the population is now our prior distribution. This is our seed for now building a Gaussian mixture model for our suspect. Right, so we show the model our data, and we adapt the model. So, and we're going to adapt, and the standard thing is only to adapt the means of each Gaussian. Right, so say we showed some data that's out here, and we then adapt the means here, and we end up having, we end up increasing the density there compared to elsewhere. Okay, the only trick I'm showing you is so if you're building a Gaussian mixture model, usually what you do is you start with a random seed. I've got 1,000 Gaussians in this. I set each Gaussian to start training my model. I have to give each Gaussian a mean and covariance and a weight. And then I show it some data, and then I adapt the means, covariances, and weight. And then I show it the data again, and I adapt the means, covariances, and weight. And this is standardly how you use expectation maximization to train a Gaussian mixture model. This is pretty much the same thing, except instead of starting from some random seed, I start my model from what I already had for the population model. Right? But ultimately, at the end of that,
But then you get a new Gaussian mixture
so
model.
I have a new Gaussian mixture model.
For the suspect.
Yeah, I have a new Gaussian. So my blue one is my population. These are completely made up. My yellow one is my suspect. Okay, now I go to my offender data, the question speaker recording. And I go get those vectors, and let's say it turns out that these vectors are, over here. I actually didn't draw that very well. I should draw some green. Okay, the yellow were there. Let's say my vectors turn out to be there. Okay, well, I can look at each of these points and say, what's the relative height of this? In this case, it's drawn as a line. What's the relative height of this line versus that line? So each one of those would be a classic calculation of a likelihood ratio. Okay, so let's say my yellow line is twice as high as my blue line. The likelihood ratio there is 2. Let me do this really simple. Okay, heights of people, 1 dimension,
Okay, nice.
right? Let's sample the heights of everybody in this room. We'll take the mean and the standard deviation, right? Population model. Let's say our sampling system was not actually taking a nice measure. Maybe we're looking at photographs of people against some sort of background, right? So we've got some measurement error in our estimates of the height, right? So let's say we now estimate the height of our suspect, and we've got some uncertainty. Or we look at multiple measurements. We look at multiple frames in a video, and in each frame, let's say we try to estimate the height. So we get a distribution, right? And let's say we've got some distribution of our estimate of the height of that individual. We actually then go and maybe we only have one value, which is our estimate of the height of the question speaker. And let's say that turns out to be here. So our likelihood ratio, what is the likelihood of this suspect? What is the likelihood of the questioned person, let's say the offender? What's the likelihood of getting this height that we think the offender is if they were the suspect versus if they were some other person from the population? That's a likelihood ratio. This is exactly the same thing. Our population was our 100 Dutchmen who speaking English. And then we built, so we've got a generative model for the 100 Dutchmen speaking English, which is representative of our population. And we've got a model for the suspect. And then we take the data points from the offender, and at each data point we can calculate a likelihood ratio. Each of these you can think of as a likelihood ratio, right? But you don't want a likelihood, okay, each of these data points corresponds to a 20 millisecond wide stretch of speech, 20 millisecond long stretch of speech. And you've got hundreds of thousands of these, right? You don't want to go to court and say, well, the first 10 milliseconds of the recording has got this likelihood ratio, and the second 10 milliseconds has got this likelihood ratio. One of the other things is we've got correlation in these, right? So you could take naive Bayes, but that's not really going to work because we've got plenty of correlation here. So the next stage in this particular model is what you would do is, let's say what we do is we take the geometric mean of these. So we take the mean of the log of each of these likelihood ratios. And we're going to treat that as a score, right? So we know we've got correlation all over the place, and we know we violated modeling assumptions, so we're not going to try and interpret this as a likelihood ratio, but we're going to take the mean of the logs of these likelihood ratios. And then we get to a second stage of modeling. So now we're talking about score-based systems. So, but this is our score. So,
So now it doesn't matter that all the assumptions were wrong or whatever.
well, it does.
No, we've got a score. And
We've got a
we
score.
Can now calculate or estimate the likely ratio
Of the score, right. Okay, so we have a score, but now we need,
where the score comes from.
now we need data to train our score-based system. So, okay, our way to do this is, okay, let's imagine we now have another set of data from another bunch of speakers. Something important, this was the offender recording. This was the question. This was in so the models we trained on the police interview condition. The data that we're putting in here are in the mobile telephone intercept condition, right? So we will have mathematical models to try and reduce the difference due to those, but we have this mismatch. We have this fundamental basic mismatch at the beginning. So we're going to get, let's say we've now got another database of Dutch male speakers speaking English, and we've got at least 2 recordings of each of them, and they're non-contemporaneous, and one is in the telephone condition and one is in the interview condition. We take the one that's in the interview condition, we use it to build a model for that speaker, a new yellow one for that speaker. We take the one that we've, right? We then take that recording of that same speaker in the telephone condition, and we calculate a score, and we take, which we know is the same speaker score, and we take all of the scores from all of the other speakers in the telephone condition, and we calculate scores for them of this first speaker versus the population. Right? And then we do the same with the second speaker. So we end up with a whole bunch of things that we know are same speaker scores, and things that we know are different speaker scores. And let's say that we end up with a whole bunch of things that we know are different speaker scores and things that we know are same speaker scores. Right? A very simple model to put onto this would be, say, 2 Gaussians with equal variance. Right? Our preferred thing to use is actually a logistic regression model. If the assumptions of 2 Gaussians with equal variances are true, then that would give you exactly the same answer as a logistic regression model. But a logistic regression model is more robust to violations of those assumptions. So that's our actually preferred model for doing this. It's a discriminative model, not a generative model, so that's it's not obviously a ratio of 2 likelihoods. This, we now go with our score that we got for the actual, this was now the suspect and the offender. So we look at the score we got for them and we say, where is that score here? Right? And we find that it's over here somewhere, and then we say, well, what's the relative height of that? What's that likelihood compared to that likelihood? And that gives us our likelihood ratio at the end. So that's one model. It's not the state-of-the-art model. This is at least 16 years old, right? But it is a standard model, and it's a way of dealing with the sort of data that we have. There are different approaches. Okay, so I'm interested in evaluation of evidence, and I'm going to skip these. Okay, there are different approaches to doing friends and voice comparison. I've been giving you a summary. It's ended up being a summary of one particular model in one particular approach. So in approaches we have, there's an auditory approach in which people listen. And they say, hey, that person pronounced red like wed. Okay, so in the question speaker recording. And our non-speaker also pronounces red like wed. I could hear that, and I have little symbols to write down so that I can actually document the particular details of the changes that I heard. And there's what's called a spectrographic approach. Okay, this is, you take a word or a phrase, and basically you turn it into a picture. And you then look at the pictures, and you say, how similar do I think these are? There's auditory acoustic phonetic. Okay, I would say this, let's say this is acoustic phonetic non-statistical approach. So some of these approaches get mixed up. So we've got auditory repeated, for example. People do both. They listen and they look at a spectrogram. They do both. So I'd say acoustic phonetic non-statistical. Somebody makes some measurements that are the sorts of measurements that people trained in acoustic phonetics make. And they take those measurements, but then they don't apply a statistical model to it. They maybe make a plot and they eyeball and they make a decision. Then we've got acoustic phonetic statistical, where you would make the same measurements, but you then put those into some sort of statistical model. And we've got, say, human supervised automatic, which is basically what I was showing you here. And traditionally, this is developed by signal processing engineers. The boundaries are fuzzy between what might be acoustic phonetic statistical and automatic. Generally, acoustic phonetic statistical, you'd expect that there's more human input in making the measurements, whereas the automatic procedure generally will just zap everything without any human input. And there's a fully automatic, but that's probably more for investigative purposes than evaluation of evidence purposes. And these are results from an Interpol survey as to what were the most popular. So it shows you that the auditory acoustic phonetic approach seems to have been the most popular. My preferred approaches would be the acoustic phonetic statistical or human supervised automatic. So the spectrographic approach, way back in the 1960s, this was called the voice print. And this is a word which very quickly fell into disrepute even among people who used the spectrographic approach. Because it was obviously coined to sound like a fingerprint. But then it was felt that it gave a false impression that it was similar to fingerprints. And the people who did use the spectrographic, there were people who had training, say, in phonetics or signal processing, speech processing, who were very critical of the people who were using this voice printing approach, because these tended to be people with no training in these areas at all, and they were just pattern matching by looking. And this was highly controversial. This is an area which is okay. These are current results from asking labs, police labs around the world, what approach do you use? And some labs said, well, we use this and this, right? But I think the basic message is that there's no one agreed upon way of doing it.
So maybe we are not there yet. Because it could be that something exists, but we don't understand that yet.
Well, I think there is what I think is the way forwards is quantitative measurement, statistical models, testing of validity and reliability. I don't think the way forward is subjective judgment-based approaches. So basically, the top three are all intrinsically subjective judgments,
So,
and I don't think that's the way forward.
why do you say that?
So
the idea of a voice print, why would it imply a kind of subjectiveness?
voice print per se was a subjective approach.
Okay.
Right. So, okay, this is an expert system. Right. Somebody who looks, let's say somebody who looks at these voice prints and says, yeah, I think it's him. I think it's the same speaker. That's not necessarily without value. Right. But what I would insist on is, okay, show me how good you are at doing this. We need some validation. We need some calibration. We need some validation. when you say it's the same speaker, how good are you at doing this? Right? It turns out that maybe it takes quite a long time for an expert to do each trial, whereas a system based on quantitative measurement statistical models, it might take quite a long time to set up the thing in the first place, but then once you've got the data and you've got it set up, it will run thousands of trials in a second, well, maybe. But the time is irrelevant, whereas approaches based on human subjective judgment often take several minutes at least to do each trial, and it becomes impractical to do enough test trials to do calibration and to do testing. So this is, again, what I think is one of the major problems in this field is that, for the most part, people are still saying, trust me, I'm an expert. Right? So that's one of the things that I'm insisting on, is that you need to do testing of the validity and reliability of your system, and it needs to be under conditions which are sufficiently similar to the conditions of the case that the results of those tests are meaningful for that case. If I test using nice, clean studio recordings, the system works wonderfully. In the real world, or something approaching real world conditions, performance much worse. Yeah. Okay, if you are using a score-based procedure, comma, the scores must account for both the similarity of the known and question sample and the typicality of the question sample with respect to the relevant population. That must be already incorporated into the score. You cannot do a distance-only measure and then incorporate that typicality with respect to the relevant population at the score to likelihood ratio calculation. And I have a paper explaining why. And I'd be happy to also talk you through it. This might be a detail. Right, but I'm now very happy because lots of people have lots of questions, and now we have the opportunity to talk. Right, so I'm sorry if I haven't answered all your questions, but that's fine if I'm here till the end of the year. So, thank you.